Hi, Dr. Hedengren. We are the Yeast Fermentation Bioreactor Group, and we are thankful to present our findings after modeling this very interesting process. So after analyzing about 30 research papers, we found a specific need in the ethanol industry. Most ethanol production is done using yeast and batch reactions, but CSTRs have the potential to increase ethanol production if some of the challenges can be overcome. One of those challenges is that bacteria compete for resources within the reactor and limit the growth of yeast. So our objective is to create a control model for the yeast fermentation reaction with an antibiotic stream in order to reduce the population of bacteria competing with the yeast.
To model the growth of E. coli, in a CSTR, we actually adapted an existing model that was already modeling yeast and producing ethanol in the CSTR. And the previous model, it had a control variable of tank temperature because the reaction is exothermic. And to manipulate that, they used cooling water. So for our model, we put in the E. coli material balance, and then to manipulate that, we added an antibiotic flow rate into the CSTR. And one of the disturbances we modeled was inlet feed of E. coli concentration changing, which wouldn't be a problem here in the US, but other countries where this could be an economical means of producing ethanol, that could be a problem.
So in order to model this process, we had to do an overall bacteria balance, which is right here. The left-hand side here is simply an accumulation term in the CSTR of bacteria. The first term here is the input of bacteria to the CSTR. Then we subtracted the exit stream of the bacteria. Then this alpha term here is the growth rate of bacteria in the CSTR. And then this beta term here is sort of the kill rate of the antibiotic. Alpha and beta are just constants that can be found in some of the papers that we found in our literature search. Along with the bacteria balance, we have an antibiotic balance here. The left-hand side, again, is the accumulation of antibiotic in the CSTR. And then this one's simple. There's no reaction taking place. It's just how much antibiotic is coming in minus how much antibiotic is leaving. Here's the original Simulink model that we adapted our model from. In this model, they had a PID controller here that controlled the cooling water flow rate to the bioreactor to keep that bioreactor at the optimal temperature. We thought we could make this model just a little bit more robust by adding in a PID controller that would control antibiotic flow rate to the bioreactor in order to keep the concentration of bacteria in the reactor below a certain threshold limit. So I've already run the simulation here. So here is the antibiotic flow rate and concentration of bacteria over time. So we wanted to see how our controller would respond to disturbances in the incoming concentration of bacteria in the inlet stream. So at time 50 here, we had a step where the incoming bacteria increased dramatically. And as you can see, the overall concentration of bacteria goes up slowly over time. And then as soon as it gets above this set point, our antibiotic controller steps in and remedies the situation. So one of the bugs that we found in our controller was that we had forgotten to turn on our anti-windup. So what was happening is when our concentration of bacteria in the CSTR was below our threshold limit, it was accumulating negative term. So that when the concentration of bacteria eventually did go above our threshold limit, it took the controller a while to respond to that increase above the threshold limit because it had such a long time in the below it.
So as David explained, when we found the bug and were able to turn on the anti-windup, our results improved dramatically from a settling time of 118 to 84, which is very significant. Not to mention the overshoot ratio decreased by a factor of 3.
In conclusion, an antibiotic feed is a feasible solution for a model, but probably not for real life, as the bacteria will probably build up resistance to the antibiotics. Recommendations would be for a model to build a model predictive controller rather than using a PI controller, as it can predict when the bacteria is going to overshoot and correct for it early on rather than later. And then for real life, to develop a yeast strain or bacteria strain that can outcompete the other bacteria. Thank you, Dr. Hedengren.